Hello, this is Muhammad Arham and my topic is drought prediction using meteorological and soil data. First of all, I'm going to give you an overview of what's the drought. Droughts are among the most severe and widespread natural disasters affecting many areas around the world, significantly impacting agriculture, water resources, and ecosystems. With climate change intensifying the frequency and severity of such events, the importance of timely and accurately drought prediction has never been greater. Recent research efforts have primarily relied on meteorological data to classify drought conditions using various machine learning algorithms. However, such approaches overlook the critical role that soil plays in the drought formation and progression. The research addresses that gap by integrating both meteorological and soil data to build a more robust and accurate machine learning model for classifying drought severity levels. Previous studies, including one notable work that achieved a maximum accuracy of 0.8625 using a random forest classifier, have focused exclusively on meteorological features such as temperature, humidity, precipitation, and wind. However, drought is a complex phenomenon influenced not only by atmospheric conditions but also by soil structure, moisture retention, and land cover. Soil data adds an additional dimension to the prediction process, potentially improving the reliability of drought classification models. This thesis proposes a novel approach by combining meteorological and soil datasets, applying feature engineering techniques, and avoiding conventional resampling method that may that may reduce the performance in overall conditions. The objective of this project is to explore and pre-process drought dataset available on internet to merge meteorological data and soil data for enhanced performance, to apply feature engineering methods to avoid traditional resampling that I already discussed, to compare the performance of various machine learning models like decision trees, random forest, SGB boost, light GBM, to evaluate model performance and analyze feature significance, to demonstrate the advantages of proposed approach over existing meteorological only models. The severity of the drought is classified into 5 classes in this thesis. The first one is D0. It's called abnormally dry. Areas are showing signs of dryness that may precede or follow a drought, so its chances are too low. That's why it's D0, abnormally dry. D1 is considered as moderate drought. Some damage to crops and pastures. Stream reservoirs or wells are low in the water moisture is too low. The third one is D2, severe drought. Crop or pasture loses likely. Water shortages are common in the D3 is extreme drought. Major crop pasture loses, widespread water shortages and restrictions. The D4, the fifth one and the last one, is exceptional drought. Exceptional and widespread crop pasture loses, shortages of water in resources, streams and wells, creating severe droughts and emergencies in the whole area. Understanding and preceding these drought categories are crucial for mitigating their adverse effects that are to be aroused in the future. Current drought conditions in the US were they have experienced many droughts in the past, the Deep Bowl of the US, and there are many more. Importance of early drought detection. Early drought detection plays a crucial role in mitigating the adverse effect of prolonged dry spells on agriculture, ecosystem, early resources, and overall economic stability. If we can predict a drought as early as possible, we can do arrangements to cover up all of these emergency situations. Unlike floods or storms, their impact may be not immediately visible, which may proactively identify the response even more vital. In agricultural sector, early warnings enable farmers and policymakers to implement timely interventions such as changing crop varieties, adjusting irrigation schedules, or activating irrigation strategies. So these are more beneficial and more good for the farmers to get a good knowledge of when and what's happening according to the data and according to the prediction of the model. While existing studies have demonstrated the effectiveness of machine learning models in drought prediction using meteorological data, there is a noticeable gap in incorporating soil data into these models. Soil properties, including moisture content, texture, the organic matter, play a significant role in the onset and severity of droughts. The lack of integration of soil data may limit the accuracy and reliability of drought predictions. To address this gap, the current research proposes integrating both meteorological and soil data to develop a more comprehensive drought classification model. By combining these data sets, the model aims to capture a more holistic view of the factors contributing to drought conditions. Additionally, to merge classes imbalance in the dataset, the drought categories are reclassified as follow. The first category, the D01, the abnormally dry, is the class 0. Then I have combined D1 and D2, the moderate to severe drought, as class 1, and then I've combined the D3 and D4 extreme to severe drought as class 2. So I've made it into 3 classes. This reclassification aims to balance the dataset without resorting to upsampling or downsampling techniques which have shown limited effectiveness in the previous studies. To conclude this research, a robust drought classification system was developed using a combination of meteorological and soil data. The primary goal was to accurately classify drought severity in the US using machine learning models, especially focusing on early indicators from soil and weather patterns. The final feature was set carefully engineered through domain knowledge and statistical reasoning, including lag features, interaction terms, and rolling averages. Among the 5 models tested, decision tree, random forest, XGBoost, light GBM, and the random forest classifier performed the best, achieving an accuracy of 0.8644. It outperformed others in both overall accuracy and class-wise balance, especially for the most severe drought classes D3 and D4. These results were further supported by macro and weighted F1 scores, showcasing the model's generalization across all drought severity levels. The project validated the importance of integrating multi-domain features like terrain, soil, weather, time, applying advanced feature engineering techniques, handling class imbalance in natural disaster data, evaluating model on realistic unbalanced dataset. The contributions that this research has made to drought prediction is to introduce a multi-source feature engineering framework combining like terrain, soil, quality, and meteorological dynamics all in one. The other contribution is designed novel features such as soil quality index, interaction matrices, and rolling weather trends to capture the temporal dynamics of drought, demonstrated the effectiveness of random forest in handling non-linear interactions and noisy features in environmental datasets, provided a detailed comparison of machine learning classifiers in a real-world drought classification problem.